So the second assumption I want to look at, and this is one that's actually extremely important in practice, and in particular in this Lalonde example, is the concern about lack of overlap in the covariate distributions. Now, if you just have a single covariate, we can do this directly. You can just plot the distribution of the two covariates. You can see whether these are very close. In high-dimensional cases, that's sort of more difficult. You could just do it one covariate at a time. But that's not necessarily sufficient. It could well be that for each covariate separately, the two distributions have a lot of overlap. But if you look at the joint distribution, there could be complicated correlation patterns that lead to lack of overlap in particular areas, and so to leading to cases to areas where the propensity score is very close to 0 and 1. So really, the way to look at the overlap is to look at the distribution of the propensity score. Lack of overlap corresponds to the propensity score being close to 0 and 1. And so you don't even need to plot the two covariate distributions directly, just looking at the distribution of the propensity score itself separately or jointly, and checking whether there's a lot of mass for close to 0 or 1, which suggests that there's problems. If you find that there is a lot of that there's concern for lack of overlap, this is the point where choosing these estimators becomes a much trickier thing. And so I want to talk about one way of dealing with that. And so, in practice, it's actually, first let me make a very extreme case. Suppose you find that there's a large part of the covariate space where the propensity score is exactly 0. It may just be that there's one group that just doesn't take part in the program. It's clear that you can't do anything for that group. You can't estimate what the effect is for that group. And so in the end, what you have to do is just put them aside, estimate the effect for the remainder of the sample, and just acknowledge that it's for a particular subsample. You can describe what the subsample is that this average refers to, and acknowledge that the other group that you can't estimate very well what the effect is for the other group. Now you can take that a little further, and you can think more generally about estimating the effect for some subpopulation here denoted by this set A. And you could think about just averaging only over the individuals in that particular subsample. And so if you look at that subsample, and you look at how well you can estimate tau for that particular subsample by inspecting the implied efficiency bound, it looks something like the expression here on this slide. And so what you can see is that it may be very helpful to rule out observations where the propensity score is very close to 0 and 1. That's what people typically do in practice already, by just throwing out either a couple or all observations where the propensity score is below some cutoff point. But so one way of formalizing that is by thinking about looking for the subsample where you get the most precise estimates. And if you do that, it turns out the optimal set has exactly the form that corresponds to what people do in practice, namely throwing out the observations where the propensity score is very close to 0 or very close to 1. In fact, it's the interval where you throw them out is symmetric on both ends. You throw out observations where the propensity score is less than alpha, as well as the observations where the propensity score is greater than minus alpha. Now, actually, you can take this a little further. You can figure out what the optimal value is for alpha for optimizing the precision. That that depends on what the marginal distribution is of the propensity score. But in practice, that's actually not all that important. And it turns out that just using alpha is 0.1, throwing out observations where the propensity score is less than 0.1 or greater than 0.9 gives you typically a much more precise estimate, and one that's very close to the most precisely estimable object. So a couple of comments on this. As I said before, this does more or less correspond to what people do in practice, but it does, in principle, change what you're estimating. Sort of after looking at part of the data, after looking at, this is without looking at the outcome data, after looking at the covariates and the treatment indicator, this suggests that you're going to be able to do much better in terms of variance by focusing only on a particular subpopulation, because the other part of the sample is not very helpful for estimating average effects. So the very extreme cases where part of the population is only in one of the two groups, if you find that men are only in the control group, not in the treatment group, it clearly doesn't make any sense to try to estimate the average effect for men. But this suggests even if there's a non-zero proportion of men in the treatment group, but it's very close to zero, you may still be better off by putting them aside and just estimating the effect only for the group where there is overlap. Okay, so now let me spend the remaining time illustrating some of these methods using the Lalonde's data that Lalonde originally used in a paper in the mid-'80s. This particular sample is from a paper by De Heja and Baba. And so this sample is actually, it's on De Heja's website, so you can look at it, look at some of these methods. It's been used in a large number of papers, including Heckman and Hodge, some papers by Smith and Todd, as well as the De Heja Baba paper. So what is the setup here? Lalonde had a randomized experiment where they had data from a randomized evaluation of a job training program, a fairly small experiment, 260 controls, 185 trainees in this particular sample. It was a randomized experiment there, so it was very easy to evaluate the effect of the program, at least to get an unbiased estimate of that effect. But what he was interested in, what makes it this very important paper in this literature, he wanted to use that as a way of evaluating how well various of these evaluation methods worked. So he said he put aside the control group from the experiment. He got a comparison group from the current population survey, as well as one from the PSID that I'm not looking at here. So he took this very large comparison group from the CPS. He said, well, let's see how well the various methods work in replicating the results from the experiment. So here, essentially, we know the truth, or at least we have a good estimate of that. Let's see how well these methods work. If we actually apply them in a setting where we don't know how well they work, they may differ, but we can't tell, we can't rank them. Here we know what the truth is, and let's see how well they work. And so, his conclusion was that none of these methods worked very well, and this sort of led to a lot more emphasis on experimental methods. So since then, there's been more. The literature has progressed, and there's been more nuanced versions of that conclusion. The basic conclusion that it's very useful to have experiments, I think, still stands very. But I mainly want to use this partly to show what the differences are between what I think would be what a lot of people would do now and what was done in that time. And so the first thing I would do looking at these data is, in addition to looking at the averages for the covariates, look at the difference in the average scaled by the standard deviation. So not so much looking at the t-statistic for whether the comparison group differs from the experimental group, but looking at the difference in the mean scaled by the standard deviation. The trouble with looking at the t-statistic is that if the sample sizes get larger and larger, the t-statistic will always get large, and that's not really the issue. The issue is how different these two groups are. And what you see is, if you look at the experimental groups, the scale differences in the means are never more than 0.2. In fact, they should all be 0, but obviously we're estimating these things, but they're all fairly small. If you look at the scale differences between the trainees and the CPS comparison group, you see these are very large. A lot of them are more than 1. There's one as big as 2.8. But sort of for the earnings variables, they're also well over 1. If you find differences more than half a standard deviation, just using linear regression by putting in these coefficients linearly, is potentially very sensitive to the exact specification. And so if you see this, at this point, the conclusion should be that that just doing linear regression is never going to work. There's no point in even looking at the results. And again, this is before we see any of the outcome data. But just doing linear regression with such big differences would rely so much on extrapolation that it's just very hard to believe that this could lead to credible results. Now, we can illustrate that another way. If we take this full sample and we do the tests for assessing unconfoundedness by using earnings in 75 as the outcome. So the actual outcome here is earnings in 78, which I haven't actually shown yet. But there's two measures of earnings prior to the program, earnings in 75 and earnings in 74. These are actually not quite yearly earnings. Things are a little more complicated, but I'll call them earnings in 74 and earnings in 75 here. And so I'm using earnings in 75 as the pseudo outcome. I'm going to treat that as the outcome, use the 7 other covariates as controls, and I'm going to use a variety of these methods that I talked about before, and see how big a difference we find for the effect of the program on earnings in 75, which we know has to be 0. This is earnings measured in thousands of dollars. And in the end, the overall effect of the program is on the order of 2,000. So there would be 2 on this scale. So if we do this for the experimental data, using the experimental controls and the trainees, looking at these 11 different estimators, they're all on the order of between 0 and 270. None of them have a t-statistic greater than 1. So this includes just taking the simple difference, which would work because we just have a randomized experiment, doing OLS with just a treatment dummy and covariates, doing OLS with separate regressions for the two groups, doing propensity score weighting, doing propensity score blocking, which I didn't really talk about, but this is another way of exploiting the propensity score by dividing the sample into strata depending on the value of the propensity score and just taking the differences within there. Propensity score regression, so where I just put in the propensity score as an additional regressor, as a regressor in addition to the treatment indicator. Matching on the propensity score, matching on the covariates, weighting and regression, blocking and regression, and matching and regression. And so here, this is illustrating the point I made at the beginning. If things are well behaved, these things should all work fine. And here they all do work fine. Now this is very different if we look at the if you use the Cps comparison group. So same set of covariates without taking the sample of 16,000 individuals in the CPS, sort of going back here, clearly are very different. But if we make this assumption, what we find is for all these estimators, we find big differences. We find big effects on earnings in 75 with the t-statistics all in the order. And now we are interested in the t-statistic. We're interested in seeing whether we find statistically and economically significant effects on this pseudo outcome. And we do. They're both statistically significant and they're substantively meaningful. They're on the same order of magnitude as the actual effect of the program. And so doing this, doing this would suggest that just using the CPS comparison group with any of these estimators would be very unlikely to lead to credible estimates. So again, this is before looking at any of the outcomes, before looking at any of the estimates of the actual effect of the program. If you see this, you should be very concerned, and you shouldn't just apply these estimators to the actual outcome data. This, in some sense, this is not surprising, given the normalized differences from the previous slide. Looking at the last column here, we see these huge differences. We should already be concerned there. Now, for the pseudo outcome, we see big effects. We should be even more concerned. So the next thing I did here with these data is try to construct a sample that had more overlap in the covariates. And so estimating the propensity score, I thought I had a transparency with the propensity score distributions, but that's not in here. I think it is in the notes, I'm pretty sure. You see that for the controls, the propensity score is very heavily concentrated at 0. It's sort of not surprising. Let me just go back for a second. That's not surprising. Most of these individuals in the CPS are very, very different from the target for this labor market program. The people who went through the labor market program had low levels of education, had very low earnings in the years prior to the program, were mostly unemployed. If you look at the CPS, individuals were making vastly larger sums of money every year. Most of these individuals, you can't imagine them being in these programs, and they clearly are not helpful for estimating the effect of the program. And the way that shows up in the statistical analysis is that for most of these individuals in the CPS, the propensity scores are extremely small. They're essentially 0, and they're only positive because of the Login model that is used to estimate the propensity score. So estimating the propensity score then, and looking at the observations in the tails, we find there's no individuals with a propensity score greater than 0.9, but there's a vast number of individuals with a propensity score less than 0.1. In fact, out of the 15,992 controls, 15,979 have a propensity score less than 1, and only 313 have a propensity score greater than 0.1. There's also a couple of trainees with a propensity score that's small. But so if we follow this recommendation of throwing out the individuals whose propensity score is less than 0.9, in this case we're throwing out a very large proportion of the data. But what we are left with is a sample that's actually comparable. A sample where you can actually where you have some chance of getting credible estimates. So let me then sort of go back to the first table, but now for this modified sample. If you look at this selected sample, and again, the important thing to keep in mind here is that the selection here is purely based on the covariates. There's nothing so far that has involved the outcome data, and so there's none of the pre-test bias issues that we often need to worry about. But here, for the selected sample, we get a much greater amount of overlap. Now the normalized differences between the two groups, and here again it's important that we look at these normalized differences rather than the t-statistics. The t-statistics obviously would be much smaller because we have a much smaller sample, but the normalized differences where we normalize by the standard deviation are now all below 0.5, with most of them being on the order of 0.2 or so between 0.1 and 0.3. And so now we have a sample where a lot of these estimators have a much better chance of actually giving us credible estimates. Now we're not extrapolating way out of sample to predict the outcomes the outcomes for the other group. Whereas before, when you're using the full CPS sample, you're essentially using these individuals with $20,000, $30,000 worth of earnings, and you're trying to predict what the earnings for the treatment group would have been given zero prior earnings. And so it's the extrapolation there that makes that analysis very low credibility. But now here, and so doing the same analysis for the 75 outcome, as well as the analysis for the full outcome, you see that for the 75 pseudo outcome, pretty much all these estimators have t-statistics less than 1.4. All these estimates are substantively fairly close to zero, and give reasonable, and so they look very reasonable here. Now, using that same sample and applying these same 11 estimators to the 78 outcome, even the simple difference here gives a reasonable number. But certainly, looking at the weighting and regression estimator or the matching and regression estimator, you get numbers that are very credible and that are reasonably precise. But the main thing here is that a lot of these estimators now work fairly well once you have a sample where they have a reasonable chance of working. So summarizing summarizing the points here, what I think is key in doing this analysis is to do a large part of the analysis prior to looking at the outcome data, checking the joint distribution of the treatment indicator and the covariates to see whether any of these methods are going to have a chance to work. That involves both looking at overlap in the covariant distributions, as well as in assessing unconfoundedness. How well you can assess the unconfoundedness is very context-specific. Often in these labor market programs, we have reasonably long labor market histories, and so these assessments have much more credibility. But if you don't have any lagged outcomes, that part is not as valuable. But only once you've established that these things are going to have some credibility, so you look at the outcome data, and then the choice of the particular estimator is of considerably less importance, though in practice, using the regression in combination with matching or weighting to improve the robustness is probably the most practically useful way of estimating these effects. Okay, so there's a question there. Yes.
You talk about the 0.5 comparison. You're talking using the word standard deviation. It seems like you meant coefficient relation. So when you were talking about the Lalonde data, you were saying that regressions won't work if the standard deviation is greater than...
Yeah, so what I was looking at there was the ratio of the difference in means to the standard deviation. So here this was just calculated here as the 25.8 minus 25.1 divided by 7, because standard deviation is pretty much the same. And so the exact way, whether you want to do the standard deviation on the full sample or the subsample, doesn't really matter. The key thing is it's not so important whether these distributions are statistically different. Looking at the t-statistic isn't very helpful. What you want to see is get a sense of whether the methods for adjusting for these differences are likely to work. And when these differences are really big, you need to be sensitive to the peculiarities of the estimators. And once these differences are big, you want to make sure, so in the Lalonde example, with the CPS being so different from the experimental group, you want to make sure you use an estimator that essentially ignores these observations with very high prior earnings. You can do that through weighting. You can do that through matching. You can do that in particular ways, but you need to be cognizant of the fact that you need to ensure that. And simple linear regression, that's the part where simple linear regression performs very poorly. Yes? Yes?
The propensity score seems to be critical to many of the estimators you mentioned, including blocking, weighting, even selecting a subsample with overlap. You mentioned that a lot of these estimators could be sensitive to the estimator for the propensity score, and that the propensity score is a difficult estimator difficult object to estimate. I was wondering what was the state of the art in terms of estimating the propensity score? How do you choose among estimators for that?
Yeah, but there's a couple of things in there. So the question was about the role of the propensity score here, and the fact that a lot of these procedures in some place or another rely on having an estimate for the propensity score and how sensitive things are to that. And so the first thing I want to do is make a distinction between estimators like the simple weighting estimator that relies very heavily on having the correct propensity score, or at least a good estimator for the propensity score, and other places where the propensity score is used, like selecting the sample. When it's used for selecting the sample, or when it's used for weighting in combination with the regression, the sensitivity is much less. I mean, in principle, the method I described would give this optimal cutoff point, but given that optimal cutoff point, the derivative is 0 essentially, and so small deviations are going to be second order. So there, the specification isn't all that critical. Now, that doesn't take away from the fact that you do need to estimate it in the end. And for the purposes it's being used for here, which is mainly trying to reduce sensitivity and trying to remove bias, rather than primarily for efficiency, I think you want to use a relatively flexible specification, which in practice means, so for what I did for the estimators I reported here, I just put in all these covariates linearly. And even then, it didn't matter all that much if I put in some quadratic terms, even though these groups were very very different. In practice, you might want to play around with that a little bit by putting in some of the higher order terms. I wouldn't be all that concerned about biases arising from this sort of playing around with the specification there, as long as you do it in this analysis prior to involving the outcome data. So, in this case, I might also have tried to put in all quadratic terms. I think there were too many for that to work very well. But I would be happy doing stepwise type procedures where you keep including covariates till the t-statistic for the next one is less than some cutoff point. So I think 2 is a reasonable number to use there. But I wouldn't be that concerned with the sensitivity there unless you're using the simple weighting estimator. Then I think you would be much more concerned, and that's partly the reason I would not recommend using that in practice. Yes?
I was looking for guidance for those of us who collect primary data. So based on your discussion, would you recommend that we do a pre-survey and collect covariate data, then try to match or collect propensity scores before launching into a full survey to look at the effect of a program?
Well, so the propensity score is sort of something that once you have the data, it's a statistical object. It's not. I mean, I think you would like to get the biases come from covariates that affect both the probability of participation and affect the outcomes. So you want to get the covariates that are highly correlated with both, or with at least with either of them. And I mean, if you actually, so you're talking about a situation where you're designing the study, but the treatment, you have no control over the actual assignment. Then the best advice, I think, is just trying to collect as many covariates as possible that affect either the probability, the participation decision, or the outcomes. And in particular, try to think hard about what affects participation, what changes incentives for participation. Because the better you can explain that, the easier it is going to be to remove biases from these comparisons. Yes? So the question is, so here we're also throwing out some of the trainees. And so at what point would I be worried that I was actually estimating the propensity score really badly? Certainly. When I did this, these particular calculations, I'm trying to recall exactly how I did this, but so pretty much I put in the covariates linearly and went with that specification. If I was doing a more substantive analysis, I would look harder at higher order terms and see if they mattered a lot. In particular here, given that we're concerned largely about the individuals having very low earnings, I would probably put in dummies sort of for being unemployed in both periods. In the end, sort of after some specification, I would just check the adequacy of the specification by looking at various covariates and see whether they differed between the two groups. But I'm not sure that I've not seen a lot of sensitivity to that in the overall results, really. I think where this is going to matter a lot, so changing the specification of the propensity score slightly is going to change the values, so that the ratios considerably in the very tail. So for these CPS individuals with very low values of the propensity score, maybe 0.01, so maybe 0.001 or maybe 0.0001, that shows up a lot in estimators that put in these weights that depend on 1 over the propensity score. If those guys are still if those individuals are still in the sample, clearly a weight of 100 versus a weight of 1,000 is going to make a big difference. But once you exclude these individuals by dropping everybody with a propensity score less than 0.1, moving the cutoff point slightly or changing the specification of the propensity score seems to have very little effect on the overall results. I mean, so in some sense, maybe what I should have done is sort of look at these tables as well, and instead of using the 0.01 cutoff, use 0.05. But sort of from having done that in a different setting, I would strongly expect the results to be extremely similar. Yes. Yeah, so I mean, that's really, sort of that's where the point came from, that in the end, once you're careful about the overlap, the differences between these estimators is much, much smaller. Now, so in the end, this is one example, and so I would still be inclined, if you do the regression, weighting the observations is still a sensible thing to do. But remember recall what the weights look like, the 1 over the propensity score. Before, with all these individuals with the propensity score extremely small, these weights get very large. Now, by throwing out these individuals with a propensity score less than 0.1, the largest, sort of the ratio of the largest to the smallest weight is now less than 10 to 1, where before it was I think, 10,000 to 1. And you clearly don't really want to have estimators where some of the observations get 10,000 times the weight that other observations get. And so here you ensure that that's not the case, but having a little bit of weighting may still make things more robust. But the difference are clearly strikingly small between the various estimators compared to what we found before.